Entropy. It pops up in chemistry and physics textbooks and confuses just about everyone at first. Is it just disorder? Not exactly. Today, let's break it down and see how it connects reactions, randomness, and even the arrow of time. In general chemistry, entropy, symbolized by a capital S, is defined as a measure of molecular randomness or energy dispersal in a system. You have probably seen it in the Gibbs free energy equation. Delta G equals delta H minus T delta S. If delta G is negative, the reaction is spontaneous. Entropy increases when systems become more randomized, like when ice melts or perfumes spreads through the air. More possible ways to arrange the particles means higher entropy. The physicist Ludwig Boltzmann defined entropy in terms of probability. His famous equation, S equals K, the natural logarithm of W, says entropy depends on how many microstates or arrangements a system can have. The second law of thermodynamics, it says the total entropy of an isolated system never ever decreases. That's why heat always flows from hot to cold, not the other way around. Entropy explains the arrow of time. The universe started in a low entropy state. Ever since, it's been increasing. That's why you can't unmix cream from coffee or unbreak an egg. Entropy is really about probability. Systems tend to move towards the most likely state, the one with the most microstates. That's why disorders happen naturally. Whether you're looking at heat engines in physics or chemical reactions in a beaker, entropy helps explains both. It's the bridge between how particle behaves and how energy moves. Now, let us review. Entropy measures energy and matter dispersal. In chemistry, it helps predict reaction spontaneity. In physics, it explains the flows of energy and direction of time. So, the next time you hear entropy, just don't think chaos. Think probability, energy, and time. Check out these full textbooks below if you want to go deeper. And remember, stay curious.